Hello, this is Dr. David Kreller of the Department of Chemistry of Georgia Southern University. This is the second video in a series of 3 videos that I'm putting together about calorimetry. In this video specifically, I'm going to talk about how we relate enthalpy changes to reaction quantities. I'll start off by defining what is meant by a thermochemical equation. You may have heard of that term and wondered, what does that mean? Okay, well, you're all familiar with chemical equation. You've seen them all the time. You've looked at them, thought about them, balanced them. And you may or may not know that this particular chemical reaction, which we're using as a specific example here, actually the combustion reaction, releases heat. This is actually the chemical reaction that occurs when you use a Bunsen burner. CH4 is the methane, or as commonly referred to, natural gas. Anyway, when this methane combusts, heat is released. And actually, that's why this is a useful tool in the laboratory. It's useful because heat is being released. We'll use it to achieve certain other things, like evaporating solvents. This is just a chemical equation. We can say, okay, qualitatively, it releases heat. In chemistry, we very often want to be more quantitative than just that. We don't want to just say, oh, there's some heat that's released. We want to talk about, okay, what's the exact amount of heat? What we have is this extra piece of information accompanying the chemical reaction. This little statement tells us that every time that this reaction occurs, there's an enthalpy change of the system of negative 890 kilojoules. This is the statement of the energy that's released, because the heat released is equal to the change in enthalpy. And now we have a thermochemical equation. This is only a thermochemical equation if we have these two parts, the chemical equation itself and this bit at the end that specifies the change in enthalpy. Enthalpy changes within systems are actually extensive quantities. It really matters on the amount that reacts. Unless it's otherwise specified, you can assume that the delta H term is for 1 mole of reaction. In 1 mole of a reaction, 1 mole of CH4 is used, 2 moles of O2 are used. 1 mole of CO2 is formed, 2 moles of H2O are formed. Those are just coming from the coefficients within that balanced chemical. Okay. Well, we'll become more familiar with these ideas by solving problems. So let's not waste any time and let's just get right into this. We'll explore this extensive property, this change in enthalpy, which is tied to the heat flow, okay, as we solve this problem. Okay, so we're told what the enthalpy change is for 1 mole of this reaction, okay? But we're told that we have 0.95 grams of sulfur. That's not a mole of sulfur, and in fact, more to the point perhaps, that's not 2 moles of sulfur. But we want to know, even though we've got some odd sort of quantity of sulfur, we want to know how much heat will be released. I encourage my students to understand that, like, all of these problems that we're solving, really when it comes down to it, are conversion problems. You might have to put on some rose tinted glasses to kind of see what I mean by that, but really it is. Really, we're dealing with a conversion problem here. You know, conversions aren't just for going between inches and centimeters, milliliters and cubic meters or things like that. Conversions happen all the time. Okay, so here we're told the amount of a reactant that we have. Well, that is ultimately going to be converted into an amount of energy, the enthalpy change. Okay, but the enthalpy change is here given to us in terms of the kilojoules of energy per mole of reaction. So we can't have grams. We actually have to convert grams into moles. So to convert grams of sulfur into moles of sulfur, we use the handy dandy atomic weight for sulfur, which turned into conversion factor, allows us to cancel out grams of sulfur and, convert that to moles of sulfur. But then up here, it doesn't say this is the enthalpy change per mole of sulfur. It says this is the enthalpy change per mole of reaction. So the next step, you might guess, is to go from moles of sulfur to moles of reaction. We'll look at the coefficient up here. It's basically telling us that there's 2 moles of sulfur every time there's 1 mole of reaction. Okay, so that's a conversion factor. It comes from the stoichiometry. So in a way, there's a little bit of an essence of stoichiometry going on here. Okay, so moles of sulfur go away, and we've now converted to moles of reaction. Okay, well now we can go from moles of reactions to enthalpy change. We use this turned into a conversion factor. Okay, so I think once you cancel the units properly, you'll multiply these numbers together and find that you're left with a number -12 kilojoules of enthalpy change. Alright, so here's another example. Okay, so we have a chemical equation, and we have the thermochemical information as well. So every time 1 mole of this reaction occurs, there's positive 128.1 kilojoules of enthalpy change. It should be delta H right up there. Okay, and so the question is how many kilojoules of heat are consumed when this quantity of a product are produced. So last time it was a quantity of a reactant. Here it's the quantity of a product. But again, everything I said last time will hold true now. So it's a conversion problem. We'll write down what we've got, 5.10 grams of hydrogen. Okay, we'll convert that to moles using the molecular weight. We can't stay in moles of any one specific reactant or product. We have to go to what? Moles of reaction. 1 mole of reaction for every 2 moles of hydrogen from the stoichiometry. Okay, and then there's positive 128.1 kilojoules of enthalpy change in the system for every mole of reaction. So again, it's the same thing, really. And this is positive 162 kilojoules of enthalpy change when that specific quantity of hydrogen reacts. Okay, so here's another question. It's the last one we'll do in this video. Well, there's a real strong similarity, but I wanted to do this one as well because when we're looking at these types of problems as conversions, it's important to realize that we're talking about a two-way street here. Not only can we convert from an amount of a reactant or product to an energy change, we can actually go the other way as well. We can be given an energy change and go the opposite way down the street, and from the energy change calculate the amount of a reactant or product. So that's what's happening here. We'll get told an energy change. 1882 kilojoules of heat are released. Okay, well we'll write that down, but this is like word math. Were released basically means we should put a negative sign in front of this. And that's from the perspective of the system. Well, we're just kind of going down the same street, but the other direction. So now, from the overall enthalpy change in kilojoules, we need to turn that into moles of reaction. We use this conversion factor, which basically comes from this statement of the thermochemical part of this equation. Every time there's 1 mole of a reaction, there's negative 6535 kilojoules. So that turns into conversion factor right there. Okay, kilojoules cancel. All right, slightly out of order in my animation. We need to go from the overall moles of reaction to the moles of the specific reactant here, C6H6, that we're talking about. Okay, so there's 2 moles C6H6 for every mole of reaction. So that's a conversion factor we need. So now we have the moles of C6H6. Okay, well, we're asked for mass. Again, this particular last step, this final step, is a step that you're probably very familiar with. A conversion of moles of a substance to mass of that substance. So of course, multiplied by the molecular weight. Okay, so once we multiply all these things together, we have this 45.00 grams of C6H6.